Andrei Negut today from MIT, who will give a brief, like 43 slides, survey on K-theoretical Hall algebras. So go ahead.
Thank you very much. It's a pleasure to give this talk, even though the format, I hope I will, I hope it will be a decent talk. Well, leaving aside the technical aspects, from a mathematical point of view, I really want to make this into a survey. And what this means is that I'll try to give you the, in a certain sense, the minimal amount of details necessary to paint a picture. So I will not be too pedantic about details. But if you want some more details or some more reading or so on, then just ask me afterwards. And there are a bunch of surveys available online, which I think are really good. Okay, so let's start with the examples, with the classical example of whole algebras for quivers. So this is following Ringel and Green. It is by now a classical story, and this is how it goes. So we let Q be a quiver. This is an oriented graph. We let I be the vertex set, and we take a field. In practice, it'll be a finite field, but whatever, for the purpose of this, this definition, it can be a field. And for a collection of integers, as you see here, then you define this affine space MV. So what is this affine space? This is, by definition, the affine space of quiver representations on the vector spaces f to the power vi. So what this means is that you assign a vector space to each vertex of your quiver, that being f to the power vi. His dimension is prescribed by this vector you have chosen. And the datum of a quiver representation is the datum of a linear map between these vector spaces associated to every edge of the quiver. And that, by definition, is a quiver representation, and MV is the affine space of quiver representations. Okay. Now, of course, you don't just care about a boring affine space. You care about the action of GLV on it. So GLV is just the product of the general linear groups which act by conjugation on the vector spaces at vertices. And therefore, because it acts on f to the power vi, it also acts on the home spaces. So you get an action of GLV on MV. And what this means is, well, if two quiver representations are in the same GLV orbit, then it means they are isomorphic. So because of that, it is natural to define the quotient stack. Curly MV is MV mod GLV, and this will be the stack of quiver representations modulo isomorphism, meaning you identify two quiver representations which can be obtained from each other by reparametrizing vector spaces at the vertices. So mod conjugation or mod isomorphism. This is the standard notion of isomorphism of quiver representations. So we care about understanding this stack because we care about understanding quiver representations modulo isomorphism. All right, and if we do that, we can construct the diagram below. So what's going on here? You have the vector spaces in the bottom, the stacks in the bottom left, MV, MV prime, and the stack in the bottom right, MV plus V prime. So the one in the bottom left, it parametrizes pairs of quiver representations V and V prime. The one in the bottom right, it parametrizes quiver representations W. And in between these two stacks, we put up here the stack of these extensions of quiver representations. So what does an extension of quiver representations means? Well, it just means, as you see here, a short exact sequence of quiver representations. The only thing you should keep in mind here is a map of quiver representations is by definition a linear map between the vector spaces at the vertices, which commutes with the edge maps. So it's the natural notion of a map of quiver representations. There's a natural notion of a short exact sequence of quiver representations. And the thing which you see here in the middle is just the moduli stack of quiver representations. I'm not going to be too pedantic about the definition of this thing. That's why I'm just writing it down as a stack in the middle so that you can see what its closed points are. But it is still defined in a stacky way, so you quotient by a parabolic subgroup and so on. Now, what's going to be interesting are these projection maps, pi1 and pi2. So pi1 remembers the quiver representations V and V prime, so the extremities of the short exact sequence, and pi2 remembers W, which is the middle of the short exact sequence. And the reason why we give this definition, or the reason why one considers this short exact this diagram, is because you want to use the extension stack as a correspondence between the moduli stacks MV, MV prime, and MV plus V prime. So let me explain how to do that. First of all, you need to associate some vector spaces to these stacks because well, that's what a whole algebra is. It starts off as a vector space. And the vector space in question is the following. Take the moduli stacks MV. Look at the closed points of MV. So MVF, this thing over here, just means the field valued closed points of this stack. And if you recall at what a definition of a stack is, MVF is just the set of quiver representations modulo isomorphism, nothing more. Quiver representations modulo isomorphism. Now, if F is a big field, then this is an infinite dimensional set. And this is an infinite set, a set of infinite size. But I will henceforth specialize F to be a finite field of cardinality Q. So then MVF is going to be a finite set. It's just the finite set of isomorphism classes of quiver representations over this field. And if you have a finite set, you can consider the vector space of complex valued functions on this finite set. So basically, what an element of this thing I call HQ is, it's nothing more than a linear combination of closed points of MVF with complex coefficients. So in other words, a linear combination of isomorphism classes of quiver representations with complex coefficients. So far, it's a vector space over C. So let's make it into an algebra, because that's what the whole algebra is. You make it into an algebra by invoking the extension diagram on the previous slide. So because you have the extension diagram, you have the projection maps pi1 and pi2. So remember, pi1 who went from the stack of extensions to the moduli stack parameterizing V and V prime, and pi2 remembered the other quiver representation, namely W. So because of that, you can apply these pull back and push forward functors on the vector spaces of functions. Now, pull back and push forward functors in general are more complicated than in this case. In this case, it is a straightforward exercise to figure out what pi1 pull back and pi2 push forward are as functions between the sets of functions on these moduli stacks. So in other words, well, let me tell you what pi2 push forward is. So if you have a function on the extension stack, and you take pi2 lower shriek of that function, then you get a function on the stack of quiver representations W. It simply sums along the fibers of the map pi2. So everything is just functions on finite sets, and the maps pi1 pull back and pi2 push forward are natural and straightforward definitions. We will see these again in the context of cohomology and K-theory if you're more familiar with that. If you're not familiar with pullback maps and push forward maps on the level of vector spaces of functions, don't worry too much about this. Just keep in mind the general shape of this definition. So you take F and G, which are functions on MV and MV prime respectively, and by applying this construction over here, you get a function on MV plus V prime, and that gives you an operation that gives you essentially a linear map from HQ, tensor HQ to HQ. The power of little q over here, it's some detail. I mean, the power is an integer which depends on the combinatorics of the quiver, and since essentially I ran out of space on this slide, I'm not giving you a definition of this, but you can find a definition of this power of q in any textbook or lecture notes on whole algebras. Well, the statement then, or the theorem, is that this operation gives you an associative product. It's an associative product on HQ as defined, and this is what is known as the whole algebra of the quiver Q. And the theorem of Ringel and Green is the following. I mean, it's not just some weird algebra. It is actually an algebra which is very closely connected with the representation theory of the quiver Q in the following sense. If the quiver Q has no loops, meaning it has no edges which start and end at a same vertex, then there is an embedding of algebras from the positive half of the quantum group associated to the positive half of the Drinfeld-Jimbo quantum group associated to the quiver Q. the parameter of the quantum group Q will be identified with the cardinality of this field. So we do have to say a few words about why all structure constants are polynomials in Q, but everything is a polynomial in Q. And what this theorem says is that you get an embedding of algebras from the thing on the left to the thing on the right. And the generator of the quantum group, which is labeled by EI, goes to the following thing: the characteristic function of the moduli stack corresponding to degree vector V, which has a single entry of 1 on one position, and all other entries are 0. So what this means basically is something very simple. A quiver representation, which is supported on a bunch of vector spaces that are 0 everywhere except for a one-dimensional space at a single vertex, that moduli stack of quiver representations is just point mod C star. So the set of closed points of that moduli stack is just a single point. There's a single isomorphism class of representation which is concentrated on which has one dimension at the vertex I and 0 dimensions everywhere else. And I'm just saying here, EI has to go to indicate her function of this one point set. And if you do that, the theorem says that its assignment extends to an algebra homomorphism, which is injective. So basically what this means is that the defining relations between the EIs in the quantum group are satisfied by these indicator functions in HQ. That's basically what this is saying, and that is a check which is one can do. I mean, I think it's quite a doable and very useful exercise. And there's one more observation there. So this map I is actually an isomorphism if Q is a finite Dynkin diagram. In affine types, it's close to an isomorphism, even though you have to add something to UQ in order to make it into an isomorphism. But in non-affine types, well, it's just an injection, and the structure of HQ is very complicated in affine types. All right, so this has been the classical definition of the whole algebra associated to a quiver. So now let's make it into a bialgebra. So it starts off as an algebra, and if you want a bialgebra, you want to have a coproduct on it. Well, it turns out that you can get a co-associative coproduct on this whole algebra just by reversing the maps pi1 and pi2. So if you look back at the definition of the product here, then you first apply pi1 pull back and then pi2 push forward. Well, if you do it the other way around, pi2 pull back, pi1 push forward, and you multiply by a suitable power of Q over here, then you get a co-associative coproduct, which is nice. But the problem is that the product defined on the previous slide and this coproduct are not compatible, meaning the coproduct is not an algebra homomorphism. And to have a bialgebra, you would want some compatibility between the product and the coproduct, which just does not happen here. So to remedy the situation, what one does, and this I think goes back to Green maybe for, I'm gonna say many decades. So the construction is very nice. What he does is he twists the coproduct, or in other words, instead of saying twist the coproduct, you can do the following thing: extend the whole algebra. So you have the whole algebra HQ, and you extend it to this HQ tilde, which is defined as HQ tensor Laurent polynomials in a bunch of symbols called psi I, which are indexed by the vertices of the quiver Q. You impose some kind of commutation relation. So obviously there has to be some prescribed interaction between X and the psi's. And the commutation relation here is that if you conjugate a certain element X by psi I, you get back X times the power of Q. And if you're familiar with quantum groups, that's exactly what happens when you conjugate an element in the positive half of a quantum group by a Cartan element. These psi I's will be nothing more than Cartan elements of quantum groups. And I think in the theory of Drinfeld-Jimbo quantum groups, they are more standardly denoted by Ki, but since I'm talking about K theory, I wanted K to mean something else. So I'm just going to call them psi I's. All right, so what we have here is an extension of the whole algebra. It's a slightly bigger algebra. And what you do is you replace the coproduct by this coproduct called delta tilde. So first of all, the psi I's are group-like, which is exactly what happens with the coproduct on quantum groups. The delta of psi I is psi I tensor psi I. And if the coproduct, which was defined up here, takes this form, sum of y tensor ZA, then the new coproduct, this delta tilde, is defined here on the right. So the summands are the same, it's just that we multiply, we put a product of psi generators in one of the tensor factors of each summand individually. So what you have over here on this line is a recipe for defining the coproduct delta tilde out of the coproduct delta. Okay. Well, you have here on the bottom the rigorous definition of what psi deg ZA is. I mean, it's just a product of psi's. And then if you do that, the coproduct delta tilde and the product become compatible. So you have a bialgebra. And the map I from the quantum group into the whole algebra becomes an embedding of bialgebras. Now, when I say that, I mean from the extended quantum group to the extended whole algebra, and the extended quantum group just means the positive half of the quantum group together with the Cartan elements. Because we know in the theory of quantum groups, if you want a coproduct, you will not get a coproduct on the positive half of your quantum group. You need to add the Cartan elements to have a well-defined coproduct. So this is the same thing that happens here. Now, what I'd like to take from this, from his very classical setup is the following. If you want a coproduct on a whole algebra, you have to enlarge the whole algebra. That is what the classical theory teaches us, and we will see this happen again in a bit. This is a good time for me to ask if there are any questions. I mean, I have just reviewed the classical theory, and if anyone has questions.
So then in general, you need this Schrick push forward will be proper. I mean, it's a push forward with proper support. Yeah.
Yes, I mean that will be the case in the more geometric cases, which we'll see in a bit. I did not worry about this kind of thing in this setup because everything was a finite set, so properness was more or less taken care of by default. The main reason, let me say it somehow differently. So the definition of the whole algebra is basically counting extensions between isomorphism classes of quiver representations. And because you're in a setup in which there are finitely many isomorphism classes of representations, finitely many isomorphism classes of extensions, and so on, everything is just counting finite sets. But if you want to generalize this picture from whole algebras to cohomology or K-theory, then this language of pi2 pullback, pi1 lower Schrick, and so on becomes very helpful. And to generalize this in a correct way, in general, you have to make sure that pi1 is a proper map. And this will be the case in the more geometric cases that we'll see in a bit.
No, in general, pi1 is not a proper map, but it's a smooth with a very nice fiber. Pi2 is always proper.
Oh, pi1, yes. Sorry, I meant pi2 is the problem was with the thumb.
Yeah, pi2 is proper. Pi2
exactly,
is proper.
Exactly.
But the pi1 it's nice, smooth. It's mostly the principal part of a nice group.
Absolutely. My apologies for mixing them up. I was looking at this slide instead of the previous one. So yeah, in this picture, pi1 pullback, pi1 is smooth and pi2 is proper. Okay, so let's move on to less classical aspects. So how do we go from one dimensions to two dimensions? So what does one dimension have to do with all of this? Well, one is the homological dimension of the category of quiver representations, which basically means that between quiver representations, you have homes and x1s, but you don't have any x2s. And from this point of view, it behaves a lot like coherent sheaves on a smooth curve. And there are actually a lot of parallels between the theory of the category of quiver representations and the theory of the category of coherent sheaves on a smooth curve. And if you want an overview, I'm linking here to some wonderful lecture notes of Schiffman, which explain all of these theories and the connections in between them. And I think it's great. But the purpose of this talk is to explain something two-dimensional. So if you want something two-dimensional, you will have to complicate these moduli stacks a little bit. So the thing we do is we want a category, or we want some upgraded quiver representations which behave like a two-dimensional category. The analogy being with coherent sheaves on a smooth surface. And the way to do that is to get something two-dimensional in that sense. And this is all just a philosophical sense. I'm not trying to be too precise. I'm not saying anything about the actual dimensions of these stacks. I'm saying something about the homological dimensions of the categories involved. So the thing you do is you replace the stack MV by its cotangent bundle, which I will denote by MV. So what does that mean in practice? Well, explicitly, MV is a very simple stack. It's defined as an affine space modulo a general linear group. You can say by definition or by the properties of the cotangent bundles of quotient stacks or whatever, the definition of NV is mu inverse of 0 modulo GLV. So what is mu inverse of 0? Mu is a map defined on MV plus MV dual. So already, we don't just have quiver representations, which are linear maps associated to the arrows in the quiver, but we also see MV star. MV star, by definition, are linear maps in the opposite direction of the arrows. So the domain of mu is not just linear maps going in the direction of the quiver, but pairs of a linear map which goes in the direction of the arrows and a linear map which goes in the opposite direction. So if XE were the linear maps associated to the edges, YE will be the linear maps which go opposite to the edges. So a point in the affine space MV plus MV star will be a collection of linear maps XE, YE, where E goes over all of the edges of this quiver. And then if you can define this quadratic map mu. It's quadratic because it's defined on an affine space, and in terms of the X and Y coordinates, it's given by this commutator over here. It takes values in the endomorphism of the vector spaces in question. So for a quiver representation, you had a vector space VI at each vertex. GLV is just the direct sum of the endomorphism rings of these VIs, and the commutator over here naturally lives in GLV. So all I'm saying is take the pre-image of 0 under this map. So what that means is pairs of XE, YE, these are called a double quiver representation because we have linear maps going in the direction of the quiver and linear maps going backwards, which satisfy the equation mu is equal to 0, which is by definition the sum of commutators in a certain sense. And then take that mu inverse of 0 and quotient it by the action of GLV because it's not hard to see that this map mu is GLV equivariant. All right, so we still have a quotient stack, but it's a little bit more complicated because while MV was an affine space modulo G, N is an affine variety modulo G, and it's going to have just slightly more complicated geometry. So here's what we can do with it. Instead of studying its whole algebra, which counts essentially sets of closed points, let's consider the Chromological or K-theoretic Hall algebras. Let me explain first what these mean. So Hall algebras are vector spaces which keep track of the numerical invariance of these stacks. In particular, the Hall algebra, which we have seen, just keeps track of the number of closed points of this stack over a finite field. It's a number, it's one of the most basic numerical invariants. But you can look at more interesting, or let's say more sophisticated numerical invariants of these stacks. For example, Homology and K-theory have been very popular in the last few decades. So the presentation I will give you of these so-called Chromological or K-theoretic Hall algebras, they follow the construction and the language of Schiffman-Vassereau, which was motivated by two-dimensional considerations, which are very, in the spirit of this talk. But I want to point out that there is a different framework to Kontsevich and Soibelman, which deals with similar algebras, but is motivated by three-dimensional considerations like a Labial threefolds. And I'm sure in this seminar you know quite a lot about this 3D viewpoint.
Maybe I just comment for graduate students. In fact, this Schiffman and Vassereau two-dimensional Hall algebra is a special case of a three-dimensional. Basically, like if you have a surface, you can construct like the total space of the canonical bundle, and it's three-dimensional. So even if you start with a Calabi-Yau, which is a total space of something, of a two-dimensional thing, you can go back. It's called dimensional reduction. So then it's not just in the spirit, it's literally Schiffman and Vasseroy is a special case.
Also, I should say that in the language of quivers, something which is more or less equivalent, I think, with what Ian said is the theory of Schiffman and Vasseroy is associated to quivers, and that of Kontsevich and Soibelman, by analogy, is associated to quivers with potential. A specific choice of potential on a double quiver applied to the three-dimensional koha of Kontsevich and Soibelman gives rise to this two-dimensional koha, which I will be studying in this talk. So even in the world of quivers, the 2D one is a particular case of 3D one. But the discussion will be a bit simpler in this talk because we will just talk about the 2D one. So what is the definition of this whole algebra? Well, first of all, we need an extension diagram. So we need a stack of extensions, V prime, W, V, those 0, with projection maps to these NV, NV prime, and then V plus V prime. The difference between this diagram and the one that you have seen before is that now NV, remember, is not just the stack of quiver representations, it's the stack of double quiver representations which satisfy the equation mu is equal to 0. So V, V prime, and W are a bit more complicated because they satisfy this equation, and they are double quiver representations. But the definition of the map pi1 and pi2 and the definition of these stacks is quite analogous. So you have this extension diagram in this case as well. So what do we replace the whole algebra with? As I said, let's take the example of the K-theoretic Hall algebra. So instead of functions on the set of closed points of these stacks, let's look at the K-theory groups of these stacks, sum them up over all dimension vectors V, and we get a vector space, I guess, over Q. If we take the K-theory with Q coefficients, you get a vector space called K hat Q. Now, I think pretty much everything in this line is explained except for this T over here. Basically, what I'm saying is I don't just want to take the K-theory of these stacks. I want to take the T equivalent K-theory of this stack. So I have to tell you what this torus T is. Well, the torus is a copy of C star. I mean, if you don't like C star, think of it as GM, but I think it makes for a little bit easier read in this way. So the torus is a one-dimensional torus C star times as many one-dimensional tori as the edges of your quiver, and it acts on the stack NV as follows. So remember, the stack NV parameterizes pairs of linear maps X and Y. This E star just doesn't do anything to the X's, but scales all the Y's uniformly. And the C star associated to a given edge E, it only affects the XE and YE corresponding to that edge, and it scales them by opposite amounts. So I'll be considering this torus action on NV. Okay, if you have this definition of the K-theory groups, then you can get an associative product, and the associative product is defined in K-theory by a formula over here. Now you might notice that I have switched my. I guess this would have also been pi2 towards Shriek. The construction is analogous to the one we have seen before. So basically, you start with the K-theory class here, you pull back here, and you push forward here. The reason why the pullback map is Shriek instead of star is that in this two-dimensional case, map pi1 is no longer smooth, but you can make it is smooth in a derived sense. So in other words, you can define what is known as a refined pullback map, and that's what this pi1 pullback is. So in the most basic case of the definition of this map, you should think of pi1 pullback as a refined pullback map in K-theory. And we will see one more example of this later on. So I don't want to go into too many details about the definitions of these maps, since I won't have time to actually give you definitions. Let me just stress that the map pi2 is proper, so we don't have any problems with the definition of this pi2 push forward. Okay, so we have an associative product, and the vector space K hat Q with this associative product is called the K-theoretic Hall algebra of the quiver Q. It is the description is very close to the one in the case of Hall algebras, at least philosophically, but care must be taken in the appropriate definition of all of these maps and the checks of all of the properties involved. So in the two-dimensional case, this algebra and its version in Homology was studied by many, many people, and unfortunately, I wouldn't have time to list everyone and all the contributions which have been made. I will tell you about Schiffman, Vasrov, Ben Davison, and Yang and Zhao, because their work is the one which is the closest to my interest. So this list is a very subjective list, and in no way should it be like any exhaustive list of the people who have worked on this. A lot of people have worked on this stuff, and probably even more people have worked on a three-dimensional version of Kontsevich and Soibelman. So I'm going to stop here because an attempt to list everyone who has worked on this is probably futile. But you know, it does have a connection with quantum groups. So with the usual Hall algebra, we saw that the Hall algebra of Q contains the positive half of the quantum group of Q. This one contains the positive half of the quantum group of the affine quantum group of Q. So basically, the way this is defined, there's a construction which is more or less due Greenfeld, I think, which is called quantum affinization. You start from a Lie algebra or a quiver or whatever Q, and you can define its quantum affinization by generators and relations. So whereas the quantum group had generators EI, where I goes over the vertices of the quiver, this quantum, its affinized quantum group had generators EIK, where I goes over the vertices of the quiver, and K goes over all the integers. So you have countably many generators for each vertex. And the assignment from UQ plus of Q hat to the K hat, which I claim is an algebra homomorphism, is the one which sends EIK. Well, let's put it in the following way. EI0 would go to the structure sheaf of the stack n sigma I. We remember that sigma I is the dimension vector, which has a single entry 1 on the ith position and 0 everywhere else. Well, this stack is very simple. It's actually point mod C star. There's a slight detail over there, but morally it's point mod C star. So if you want to write down a K-theory class on point mod C star, you don't really have much of a choice. So basically, the K-theory of point mod C star is just Courant polynomials in a single variable, which I call curly L. And therefore, the assignment over here sends EIK to the kth power of this variable L to the power K. So L is just the tautological, if you will, line bundle on point mod C star, and EIK goes to the K-theory class of its kth power. There are a lot of Ks in this business, but I think this definition makes a lot of sense once you convince yourself that a stack N is point mod C star in this case. So you get an algebra homomorphism, and the K-theoretic Hall algebra is just going to be something bigger, some bigger algebra. How do we understand it? Well, remember how NV was defined. So it was defined as essentially an affine subvariety of affine space modulo GLV. So T star, so MV was affine space, T star MV is affine space times affine space. And you had this mu inverse of 0, which is essentially cut out by a bunch of polynomial equations. Now, because you have this closed embedding, well, actually, I was going to say that next. So because you embed into affine space modulo GLV, you can certainly understand the K-theory of affine space modulo GLV. So you have this chain of identifications. The K-theory of affine space modulo G is torus times GLV equivariant K-theory of affine space, and affine space has boring K-theory. So it's just the T times GLV equivariant K-theory of a point. So let's put some coordinates and describe the T times GLV equivariant K-theory of a point. So let Q and QE denote the elementary characters of the torus T, which remember was C star times as many C stars as the number of edges. And let's take a maximal torus of GLV, call it TV, and let's denote the elementary characters of this maximal torus by ZIA. So I goes over the vertices of the quiver, and the number A goes from 1 to the dimension of the vector space at the I vertex. So this number called VI. Then, you know, it's an elementary isomorphism that the T times GLV equivariant K-theory of a point is Laurent polynomial ring in all these variables, and you take invariance under a symmetric group. So explicitly, W is a product of symmetric groups, which acts by independently permuting the symbols ZI1 ... ZIVI for all I independently. So there's no mixing of ZI and ZI prime, but this symmetric group acts by permuting the ZIAs for fixed time. All right, so this gives you a very complete, I would say, description of the T star GLV equivariant K-theory of a point. So in other words, the K-theory of this big thing over here. So what about K-theory of NV? Well, there is the Thomason localization theorem in equivariant K-theory. And it basically says that if you localize, meaning that if you tensor with the fraction field of this big ring, so in other words, yet again, if you work over rational functions instead of Laurent polynomials, then the localized equivariant K-theory of NV, the thing we want to study, is isomorphic to just the vector space of rational function in these many variables, and you take a Weyl invariant. So by doing this localization procedure, you lose something. I mean, you lose interesting information of the torsion. Your actual K-theory will be an integral form inside this big fraction field of rational functions, but at least at first approximation, this localization theorem, this localization isomorphism is useful. So right now, this thing is an isomorphism of Q vector spaces. And of course, we would like to make it into an isomorphism of algebras. So in the context of two-dimensional K-theoretic Hall algebras, Schiffman and Vassereau said, you know, if you want to make this map I lower star an algebra homomorphism, you have a multiplication here. You have to put a multiplication on these big vector spaces of rational functions. And this multiplication is exactly what people call a shuffle algebra. Now, shuffle algebras had been studied before in various contexts. I mean, it's a classical object. It goes back many decades, but in the theory of quantum groups, I would say it has been first studied by Fagin-Odesky and then studied by Enriquez, Hutchinson-Baliuk, and many other people have studied shuffle algebras in various contexts. But in the context of two-dimensional cohas and khas, the question is how to make this field of rational functions into an algebra so as to match the K-theoretic Hall algebra. And this idea is not particular to the two-dimensional case. Shuffle algebras and also connected by Kontsevich and Soebelman with their three-dimensional cohas. So it's the same kind of picture appears in all of these points of view, but you know, I will just talk about the two-dimensional cases. All right, so how do you define the shuffle product? So first of all, you take all of these vector spaces of rational functions, you sum them up over all choices of V. So remember, V is just the vector of VI's. So basically, these are the vector spaces of rational functions in arbitrarily many variables, and you make it into an algebra by the formula down here. So what does this formula mean? Well, it looks a bit scary at first, but I'll try and break it down. So F is a rational function in V variables. G is a rational function in V prime variables. And you want your answer to be a rational function in V plus V prime variables. And the way you do that is you apply F to the first V variables, you apply G to the next V prime variables, then you have a rational function in V plus V prime variables, but you want a symmetric rational function, so you symmetrize it. And this same over here just means sum up of all possible permutations of these variables. Now, the one other thing in this formula is this funny function that you see here called theta. So if you did not have this factor theta here, the shuffle product would be commutative and rather boring. What this function theta is, it's a particular rational function which depends on the shape of your quiver. So it's going to be a product of linear factors of the form 1 minus z divided by z prime times some product of q's, and the shape of this product is forced upon you by the shape of the quiver. So it's it's an explicit formula. If it doesn't mean much to you at first glance, then I can't blame you. All I need to say about this is that these particular linear factors in this formula are forced upon you by the shape of the quiver. They are encoded in the combinatorials of the quiver. So you stick this rational function inside this product, and you get something which is known as the shuffle algebra. In other words, VQ, which is a vector space, endowed with this shuffle product, is what people call a shuffle algebra. So for historical completion, I should say that Fagin and Odesky studied an elliptic version of this, which was associated, I think, to finite quivers. This here is just a natural generalization of their construction to an arbitrary quiver, and is a trigonometric generation of their elliptic construction. So I would say it's a variant of the one studied by Fagin and Lodesky. Okay, so if you put this this multiplication on the shuffle algebra, then the localization isomorphism, which we have seen here, down here, this localization isomorphism becomes an algebra isomorphism. In other words, this slightly weird at first shuffle product, which I defined on the previous slide, is rigged in such a way that this map I lower star be an algebra isomorphism. So the shuffle product and the K-theoretic product given by the extension diagram are compatible. And that's very nice, because this gives you an explicit way to understand the K-ha. I mean, it is a localized version of the K-ha, so it's not as good as the K-ha itself, but at least it gives you a very explicit description of the K-ha in terms of some functions. And what's really nice about this is that the shuffle algebra point of view also allows you to put a coproduct on the K-ha. But just like before in the classical case, it's not really on the K-ha. We need to extend a K-ha. And moreover, it's not really a coproduct, but it's a topological coproduct because it's going to be given by infinite sums. So, you know, modulo these caveats, you do get a coproduct, but one should be aware of them. So this is the theorem of the construction of coproducts. So this is a definition I gave for the cyclic quiver, and it was generalized Yang and Zhao afterwards. They actually were much more interested in the connections of these constructions with kohas and khas at the moment. My definition of this coproduct on shuffle algebras was motivated by completely different considerations, which is very nice because it shows how these things actually pop up in a variety of contexts. So I was much more interested in the study of shuffle algebras in a more quantum groupy kind of way, like Fagin and Lodesky and all of the others did. But it was later observed Yang and Zhao that the definition I had for the coproduct is useful in the context of K-theoretic and Chromological Hall algebras as well. So here's how you define this coproduct. So first of all, you have to extend your shuffle algebra. So before, we had added symbols called psi I. Now we have to add infinitely many symbols psi I for each vertex of the quiver. So these symbols we add are called psi I k. I goes over the vertices of the quiver, and k goes over the non-negative integers. And you impose a relation over here. Now this relation is the k-ha version of the one that you saw for Green's coproduct. It's a formula which says how you commute an element of the shuffle algebra with a psi. Well, you commute it, but at the cost of a bunch of rational functions. So psi j of w here is just the generating series of the psi I k, so psi j k, whatever. So anyway, leaving formulas aside, these formulas are forced upon you, so there's no choice here really. The extended shuffle algebra is the shuffle algebra together with these symbols, and there's a prescribed commutation relation for moving psi's to the other side of the shuffle algebra. And here's how you define the coproduct. The coproduct of the psi's is group-like in a generating series kind of sense. And the coproduct of an element of the shuffle algebra is defined as here below. So this formula may be scary, but here's what it means. If f is a rational function in v variables, you want to get a tensor out of it. You want to get a tensor of rational functions in fewer variables. The way you do that is you split up the variable set. You split up the set of v variables into w variables and v minus w variables. And you break up the function f by putting a tensor product sign in between and all the first w variables on the left and the last v minus w variables on the right of the tensor product sign. Now, if f were a polynomial, this would be unambiguous. But f is a rational function, so you must ask me, what does it mean to take a rational function and put some of its variables to the left of the tensor product sign and some of the variables to the right of the tensor product sign? So what it means is the following. You expand this rational function in the limit when the first w variables are much smaller than the last v minus w variables. You get a power series, and for each term in that power series, you put a tensor product symbol in between the w variables and the last v minus w variables. And you know, because you expand as a power series, you don't get a coproduct, you get a topological coproduct because it's an infinite sum. And just like in the case of green, you have to stick these psi symbols over here. Otherwise, the coproduct will not be compatible with the product, because the gist of this construction is that the coproduct defined over here and the shuffle product defined on the previous slide make V tilde Q into a bialgebra. And here you go. Now you have V tilde Q is a bialgebra, and this also makes the localized KH into a bialgebra. Of course, it would be extremely interesting to completely understand what this looks like on the actual KH, not on a localized one. I mean, there are some issues of torsion and so on, but I will sweep these under the rug. If you assume that a KH injects into localized KH, which I think everybody believes, then this construction induces a coproduct, a topological coproduct on the KH as well. But the construction is naturally shuffle languagey, so it takes part on the shuffle algebra side. And over here on the bottom, I'm saying the upshot of this, the same moral as we have seen in the case of a green coproduct. To be able to make whatever whole algebra, K-theoretic whole algebra into a bialgebra, you need to enlarge it by adding Cartan elements. In the classical case, you added finitely many Cartan elements. In this more affine-like case, you add countably many Cartan elements for each vertex of the quiver. All right, I have a couple more slides which have to do with a global version of all of this. But if anyone has any questions on what happened in the last few slides, then now's a good time to ask.
So in the remaining slides, will you consider geometric examples?
Oh, yeah.
Okay. So
in the next few slides, I'll be talking about a generalization of this to surfaces. And quivers are
before you go into surfaces, there are also curves.
That is true, but since I'm motivated by a two-dimensional example, I'm going to focus on surfaces. You can do versions of these things for curves. They are simpler. I mean, you can give all of these definitions.
It's an interesting question. Do you know, even in cohomological setup, what will be coha for, say, projective line?
Do you mean the actual coha or the
yeah, the actual or K-theoretical? It's all right.
I would say, well, in cohomology, we know that I think it's known. I'm not sure if Ben Davison or Schiffman and Vassaro proved this. The KH is torsion-free, so that means that it embeds in the localized coha. So people know these torsion-freeness results in cohomology. They don't know them in K-theory. So in cohomology, at least, the actual coha embeds in the shuffle algebra, and it's a wonderful question to describe the image of this embedding. So we don't understand it in general, unfortunately. I have some results about how to describe the image for a cyclic quiver and a Jordan quiver. I think everybody believes that the images in finite and affine quivers are given by the so-called wheel conditions. It's something I won't have time to describe, but in wild types, nobody knows exactly how to describe the image of the KH in the localized KH, i.e. inside the shuffle algebra, and it's a wonderful question, but it's a very hard question. Now, your question was for P1. I think probably it should be easier for P1, but I don't have an answer off the top of my head. So I mostly study surfaces. I mean, I can tell you what the answer is for A2 on the next slide. If,
okay, go ahead.
A2 and P1 are both reasonably simple. So what is this saying?
Actually, on Jan's question on the P1, so on the arithmetic side, it's also kind of corresponding to curve.
Okay.
In a dedicated domain, yes, in a dedicated domain. So have you seen anybody consider this?
I'm not sure I heard you. I'm sorry. I can't.
Zhongzhu, the sound it's a bad line. Can you come closer to the microphone?
Okay. Is it better now?
Yep.
Okay. Thank you. So corresponding to the one-dimensional smooth curve is the arithmetic. Say, giving a number field, you have algebraic numbers, which is a dedicated domain, and it's which corresponds to smooth one-dimensional variety projective. So any kind of corresponding Hall algebra, do you know anybody who considers this?
No. For the usual Hall algebras, it started with Kapranov, and then Schiffman, Kapranov, Vassero. And they indeed described it in terms of, like, you know, this sort of kernels. And you have kernel for any curve. So yeah, there are some answers, but for constructible Hall algebra, for cosmological, I don't know.
Well, it's actually extremely interesting. There's a paper of Schiffman and Vassero, and this was also explored by Burban and Schiffman. The constructible Hall algebra of a genus G curve is connected with this K-theoretic Hall algebra of the G loop quiver. So the quiver with one vertex and G loops, they are not quite the same. I mean, I think you can identify them in the case when G is equal to 1. For arbitrary G, there is a connection in between them, which was explored by Schiffman, Vassero, Kapranov, and it's quite an interesting connection. But on one side, you have the constructible Hall algebra, and on the other side, you have the cohomological version. So they are different objects, but the same constructions more or less apply to both. And actually, you can see this on this slide. So in the case when Q is a Jordan quiver, so one vertex and one loop, it turns out that the stack I call ND is the same thing as the stack of sheaves on the affine plane. The length of
why plane, not just line? It's torsion sheaves. It's kind of torsion sheaves on the line. It's you have representations of the polynomial algebra.
But ND is a double quiver. So
it's a double, yeah.
So ND was the one with a single quiver, and ND was a double quiver.
See.
Yeah.
Okay.
So because it's a double quiver, it corresponds to finite length sheaves on the affine plane, and you know, you can ask these kind of questions for an arbitrary surface instead of the affine plane. So the affine plane case is completely answered by the previous philosophy, but now you can take any smooth surface S and ask for the following thing. So take the direct sum of the K-theories of the stack of finite length sheaves on the surface S. So, well, you sum over D, where D is the length of these sheaves. You get a vector space. Let's call this K of S. Can you make this into an algebra? And well, it actually is a problem which has only been very recently solved in a rigorous way, even though the intuition and the philosophy had been known for quite a while. So here's a definition of what the shuffle algebra looks like. So, you know, we saw previously that the K-theoretic Hall algebra and the shuffle algebras are counterparts of each other. They are isomorphic after localization. But it turns out that there's a notion of shuffle algebras associated to surfaces, and here it is. So take your surface S, and instead of having those big vector spaces of rational functions, the shuffle algebra is defined as the direct sum of the K-theories of the powers of the surface. But it's not just the powers of a surface. If you look here, it's actually surface mod C star, where C star acts trivially on a surface. Now, a K-theory of something mod C star, where C star acts trivially on that something, is just K-theory of something tensored polynomials in one variable. Since here you have D factors of C star, you would have here the K-theory of S times S times S times S, polynomials in variables Z1, Z2, ... ZD. And these Z's are the counterparts of the variables that we have seen a few slides ago for the usual shuffle algebra. And the condition that everything be symmetric is captured in the fact that we don't take the K-theory of this power of the surface, we take the equivariant K-theory with respect to the action of a symmetric group of size D. And the definition of the shuffle product is inspired by the one you saw before. So basically, if F is a K-theory class on S to the power D, and G is a K-theory class on S to the D prime, then you construct this thing here, which is a K-theory class on S to the D plus D prime. So F exterior product G is unambiguously a class on S to the power D plus D prime. You have to multiply with these beta functions. So previously, in the quiver case, beta functions were just some explicit rational functions which depended on the surface of the quiver. In this geometric case, zeta over here is a rational function valued in the K-theory of the product of a surface. And what it is explicitly, well, the exterior power here with the variable x of the structure sheaf of certain diagonals. So for every index which is smaller than d and every other index which is bigger than d, this function's theta a prime will involve the a prime diagonal inside some power of a surface. So this here is a global version of the shuffle algebra associated with quivers, and it's something I defined for surfaces a few years ago. And you know, and even when I studied this, I wasn't actually looking at K-has in particular, but the connection with K-has actually came, well, I would say a couple of years later, so namely last year, if I have my chronology correct. So what is the connection between the K-ha of S and this particular shuffle algebra, which I defined? Here it is. It's a theorem of my student, Yu Zhao. So it's not the same Zhao as before, he's my student. And it is a wonderful theorem, I think. This is what Yu Zhao says. It was expected by the philosophy of these extension diagrams and so on, it was expected that you can put an associative product on the K-ha of S. So the K-ha of S is defined on this slide. It was expected that you could put a product on this K-ha by doing this kind of pull-push construction. The problem is that the map pi1 not being smooth, you have to be careful about this refined pullback. And Yu Zhao found a particularly nice definition of this pi1 shriek using refined his in maps, and then he checked associativity and he checked a lot of things about his construction and everything worked out. So in other words, he rigorously did what was expected from the general philosophy. And moreover, and this is actually a connection with the shuffle algebra I defined on the previous slide, there is a map which is pretty much like the embedding of a fixed point set, but not quite. There is a map from the dth power of S mod C star to the stack of length D sheaves on S. And Yu Zhao observed that the inverse of the localization isomorphism, which a priori is just an isomorphism of Q vector spaces between K-ha log and VS, is also an isomorphism of algebra. So he observed that the K-theoretic product, which he rigorously defined based on the pre-existing philosophy, is isomorphic with the shuffle algebra product, which I defined on the previous slide. And you know, at least in the case of localization, everything I would say is very nicely captured by this description. Well, yeah. I mean, you know,
Andrei, but what this paper by Kapranov and Vassero, although it's homological.
That's my next slide.
Ah, okay.
That's my next statement. So, so more or less, there was an independent proof of this kind of construction, which was due to Kapranov and Vassero, and their proof was actually technically they proved more than what Yu Zhao proved, because they were able to define this K-theoretic Hall product not just on the stack of zero-dimensional sheaves, but on the stack of 0, 1, and 2-dimensional sheaves. So they did more, essentially because they use a more high-tech technology. But philosophically, both the construction of Yu Zhao and the construction of Kapranov-Vassero boils down to properly understanding and defining these refined pullback maps in a certain context. So Yu Zhao worked with refined pullback maps in K-theory, and Kapranov-Vassero worked with DG schemes, and that's why they were able to prove a more general statement. But the two constructions are independent. And actually, I think they came out on the archive with weeks of each other. So, but I stated Yu Zhao's theorem first because, well, one, he's my student and it's my responsibility, and two, he connected his point of view with shuffle algebra by this localization isomorphism over here. So he connected his construction with the one I had found a couple of years earlier. So it's a nice thing when a lot of things you have been working on are connected in this way. And actually, after Kapranov and Vassero and after Yu Zhao and so on, Horta and Sala, they actually extended the constructions above to I would say the highest conceivable level of abstraction known to humankind. So instead of working with K-theory and with DG schemes and so on, they replace K-theory by the infinity categories of complexes on a derived moduli stacks of coherent sheaves. So it's a much more advanced heading, which subsumes the K-theoretic construction as previously. But once you strip all of these technical complications, then all of these constructions essentially boil down to properly defining the pullback map in such a way that you can prove associativity. And this is what essentially all of them did in various languaes. All right, so this has been my talk.
Just a second.
Thank you very much.
Is this isomorphism is just as algebra or as Bialgebra?
Well, the problem with Bialgebras, I don't really know what a good counterpart for the coproduct is in the case of the surfaces. And I mean, we have some candidates, but I'm not sure what the best one is for the following reasons. So in the quiver case, let me actually move back here. So in the quiver case, you don't put the coproduct on the shuffle algebra, but you enlarge it by adding as many generators as as vertices of the quiver and as non-negative integers. But in this case, you would have to enlarge this algebra VS, and I'm not sure what is a geometric context to perform this enlargement. So if the K-theory of S, if for example S were something like a rational surface and you had QNet decompositions, then I would say, yeah, enlarge it by symbols psi ik, where I goes over a basis of the K-theory of S, and then you can essentially do the same construction over. But I don't want a construction which uses QNet decompositions in K-theory because those are very rare. I would like a construction of this coproduct which is more geometric in nature, and I don't have a good understanding of this yet.
In the higher dimension, definitely there is a problem because
the
compatibility really relies on the dimension one.
It's even the definition. I mean, you can intuitively make some definitions, but I think it's a problem of having the right language to define this coproduct in K-theory. So once again, in cohomology, because you have QNet compositions, then the natural analog of the quiver coproduct would apply. You choose a basis of cohomology, and you just have these psi ik's where I goes over a basis in cohomology, and more or less the same definition works. But in K-theory, I don't want to do that because I don't want to assume QNet decompositions in K-theory. And I don't have an understanding of the coproduct which does not use these QNet decompositions. Thank you very much.
Thank you. Are there any questions? Okay, so I have a couple of questions. One is sort of rather philosophical. If you want to go up in the dimension, you started with dimension 1, then now you're in dimension 2. Well, considering only zero-dimensional sheaves, but Kapranov and Vassero kind of did it for sheaves supported on curves and on the whole surface. Now, if you want to go to the dimension 3, so there are some problems, like that your stack has to be symplectic shifted. I mean, which means that instead of just a variety of dimension 3, you should have Calabi-Yau. And this means that, from the point of view of this, whatever Porta and Sala did or other people, you need to add additional data. In this case, it's a constructible sheaf. It's a sheaf of vanishing cycles with the potential of this Calabi-Yau. Now, if you go to the dimension 4 and 5, I mean, certainly that's all started with the purpose to give meaning to certain, from physics perspective, indices like Donaldson-Thomas invariants and blah, 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 yeah? All right, so there are some interesting counts for four-dimensional Calabi-Yau, and from the perspective of Kunkov and others, you also see five-dimensional. Like, for example, taking total space of the rank 2 Okay.
Oh, yeah.
Well, all right. So if you want to generalize to higher dimensions, what additional data should be taken?
You know, if I were giving this advice, I would start, you know, always try and understand the higher versions of the shuffle algebras, because the shuffle algebras are something you can write down in any dimension. I mean, you can definitely write down a big algebra of rational functions with a product. Now the question is, can you study it? I mean, for example, in the case of A3, of equivalent A3, the corresponding shuffle algebra is much more complicated than in the case of A2, which is the shuffle algebra that we've seen in this talk. And these kind of shuffle algebras were explored by Hakoncevich and Soibelman. I mean, I would say they're difficult to study because even though their definition is clear, studying properties of them is kind of hard. So I'll give you an example of a property which you can study. So I have I actually did I actually worked a lot when I was in grad school to establish the isomorphism between the shuffle algebra and the quantum affine group in the case of the cyclic quiver. That was a conjecture of Fagin that, you know, he conjectured that these two objects are isomorphic, and it's something which you actually had to write a couple of long papers to prove them. And that was only in the case of the cyclic quiver. If you generalize this to other quivers, or if you generalize it from the two-dimensional shuffle algebras to three-dimensional shuffle algebras, then I wouldn't even begin to imagine how you could prove such.
Yeah, but even for 3 dimensions, I'm looking at your definition, and you know, you use just roughly K-theory of some kind of very simple stacks, but for cohomology, you should take the coefficient cohomology of something, some variety or stack with coefficients in the sheaf of vanishing cycles.
Yeah, I mean,
I don't know the K-theoretical version of this.
Well,
So
there is I mean, you probably don't know about this, but there's recent work of Tudor Pădurariu, who has graduated from MIT, and he gave a K-theoretic version of what I think is the
quiver with potential. Okay. Right.
And I think he and Ben Davison even proved that the dimensional reduction result in K-theory. And I have to say, these kind of dimensional reduction results which say that certain examples of three-dimensional cohas are actually isomorphic to two-dimensional cohas. I would say those were, for me, a demotivating thing from studying a lot of these things in 3 dimensions, because we had the results say is that...
Well, you should say that to Ben, because
I mean, I'm saying, I mean, they proved in a certain sense that had a certain class of 3-dimensional cohas are actually the same as the 2-dimensional cohas, but you have to make some specializations to make this to hold.
Yeah, but for
some kind of torus.
Okay, so then next question. For me, it's rather the way to you know, this cohomology or whatever with coefficients in the sheaf of vanishing cycles
of course.
is basically impossible to compute, and so this dimensional reduction get rid of the potential, and so it reduces to sort of shiftment. So for me, it's a computational story. But why shuffle algebras? Why they kind of naturally appear
as Yu Zhao explained in his paper, in the case of surfaces, they naturally appear because the moduli stacks in question has a fixed point set which is isomorphic to a certain power of the surface in question. So
okay.
It's a geometric connection.
I see.
In the case of in the quiver cases, I mean, I'm sure it was observed by Schiffman and Vasro. I can't think of the paper, but I think it goes back to them, that the shuffle algebra connection comes from this embedding over here, and that the stack which defines the K-ha is embedded inside a big old affine space modulo GLV. So that's why shuffle algebra appears in the quiver case. So
Actually, there is one more structure which kind of I'm wondering in. It's a structure of factorization algebra, which Kevin Costello likes very much. And with Maxime, we observed this kind of a structure which comes exactly from the action of the tori. So if you consider representations of say, of a quiver of different dimensions, and if you take equivariant K-theory, yeah, so it's a module of the equivariant K-theory of a point.
Yep.
Which means that it's a coherent sheaf on the configuration of points on the torus.
Exactly.
And you have it for every dimension. So then you have a collection of coherent sheaves on these configuration spaces, and they somehow compatible. They satisfy certain property, which is basically the property of factorization algebra. And somehow this is intrinsic. And from this perspective, appearance of shuffle algebras is kind of more natural, because you have these parameters, whatever shuffle parameter, the historic weights, they are built in.
Yeah, that's another great explanation. Yeah, I agree.
Okay, more questions?
Yes. So here, probably Lustig's, probably first is a common Lustig's work here probably should be mentioned in the sense that when you look at the K-theory, basically given the space and the K-theory is arriving really, and it's from the category of equivalence vector bundles, and you establish your K-theory of the variety. And what the Lustig did was you still have this variety, and you also have the group action. So instead of looking at the K-theory, looking at the constructable shifts, and within he constructed this a very nice category of semi-simple complexes and perverse shifts. And then you take this shift function correspondence going down to the finite field that somehow recovers the Ringo's whole algebra construction. So this is where the geometrical construction, probably the earliest geometrical construction of the whole algebra started.
I agree. So in a survey over here, in a survey I'm listing over here, which has his viewpoint, it's a survey of Schiffman. He explains that he explains the connection between this stack, which they work with, T star and V, and some kind of Lustig nilpotent varieties for the quiver in question. And I don't think they give isomorphic objects, but they are definitely philosophically similar. So, yeah.
Well, actually, Lustig provides more than just a computational first, because given this, it's a categorification of whole algebra.
Right. Yeah.
And because of this category are all semi-simple, and you just take the grothendieck group. This is how exactly he constructed the whole algebra. At each level, you take the grothendieck group of that category, and on the function level, you are doing this. And what he was doing, these are actually functorial. This pi2 shrink, low shrink, push forward, pull back. These are all on the categorical level. So given the category, you have something which is standard, simple objects. So they gave simple objects always form the basis of this grothendieck group of the category. So that's what the canonical basis was constructed. So in this case, when you look at the K-theory, and the sense of a canonical basis seems to be in the computational, in this business seems to be missing somewhere. So have you thought of?
Not me personally, and actually I'm not really sure. I know of anyone who studied the analogs of these.
No, but it's not completely missing. You can, what actually Lustig does, he has some category, he considers stack of objects, whatever, and he consider like constructible sheaves with certain conditions on the support. So then you can do it in the setup of coherent sheaves. You can look for stacks of objects. Maybe this is what Porta and Sala did. I did not really read the paper. You have this DG stack of say, coherent shifts of dB of coherent shifts on the surface, and you can consider, yeah, on the stack. So probably you categorify. I think the title of their paper includes categorification of Koha. Am I right?
Well, yeah, I mean,
so they just replace constructible shifts by coherent shifts, and so if you're kind of very persistent.
Actually, yeah, I'm curious with the categorification of Koha. So is that in a sense that the cohomology ring is categorified? Because you are using a cohomology ring of this modular space, and then you put them together, you form the cohomological Hall algebra.
I mean, clearly, if you start with the K-theoretic Hall algebra, then a standard categorification, as Ian says, is that kind of, well, derived category in some kind of infinity category sense. But it seems like you're asking specifically for the Koha. If you can take this kind of construction in cohomology and categorify it by some category of perverse sheaves and so on.
So I mean, so for example, for taking just the Jordan quiver, and for a single and giving a fixed dimension vector, you have this modular space, and you take the equivalent homology ring. So when they do the categorification, what do they get, and how do they realize this homology from a categorical perspective?
So Horta Tayasala, at least, they don't set out to categorify cohomology. They set out to categorify K-theory. So a category for them is a derived category of a stack. So a stack of double quiver representations which satisfy a certain quadratic equation. So it's an explicit quotient stack, and they consider its derived category in an infinity category sense. That is the place which they work with. But it should be naturally thought of as a categorification of K-theory, I would say.
I see.
It seems to me
I would definitely curious how the cohomology ring is categorized. So
yeah, I mean, I would say in this line of work, people don't really think about that language. I mean, you could definitely ask what would happen if you if you replace the cohomology with categories of perverse sheaves or so on. I've never thought about this kind of thing. I'm not even sure if it's a well-posed question or anything, but definitely I don't know anyone who has studied that case in this line of work. I mean, it's mostly people are interested in K-theory because it is very straightforward to categorify, I would say.
Okay, more questions? Okay, if there are no more questions, let's thank Andrei for
thank you very much.
Talk. Thank you.
It's been a pleasure.
Thank you, Andrei. Very good talk.
Thank you very much.
Thank you.